This clip is going to focus on making free body diagrams. So I'll use FBD for free body diagrams. This is something that you've probably done in high school. I want to make sure that we get a few pieces of it right, particularly with regard to moving in the direction of dealing with rotational motion, where how you make the free body diagram probably matters more than when you're just dealing with particle motion. So let's start with talking about what a free body diagram is and what the idea of a free body diagram is. And really, to think about what is a free body diagram, I think it's maybe helpful to remember back to ModSim, to this idea of abstracting, and also to the idea of deciding what your system is, so kind of where your system boundaries are. So in some ways, a free body diagram is a lot like a stock and flow, in that it basically is a way of defining kind of how many things you're thinking about in this system and how stuff is affecting the things that you're thinking about. Okay, so let me just I'm going to do an example of a free body diagram, and as I do the example, I'll highlight what some of the issues are. So the example I'm going to do is I'm going to think about a bicycle, because I like bicycles, and sometimes I can draw them. And there's someone that's riding on the bicycle, right? So they're riding along on the ground and working very hard, having a wonderful time. And we're interested in trying to model the motion of this biker on the bicycle. So how are we going to think about doing that? Well, the first thing we have to do, if we're going to model the motion, is try to decide what level we're going to abstract at. And I would be inclined to sort of, start as simple as possible. So I'm going to abstract by thinking about this whole thing, the bicycle and rider, as being one system. And also I'm going to think about that system as being a single point mass. So I'm going to abstract that whole thing, the bicycle and the rider, I'm just going to compress them on down to a single point mass. Right? And what that means then is that if I were to sort of draw a system diagram here, I would say I'm thinking about this whole thing, bicycle plus rider, as one chunk. Right? I only have one chunk in the system. So it's one chunk, and I'm not thinking about rotation. Now, it's often the case that people will, when they go from this and they say, okay, it's one chunk, I'm not thinking about rotation, they'll start to just use a dot to represent the free body diagram. And I actually don't think that's a great idea. Personally, the reason I don't think that's a great idea is it sort of disconnects you from thinking about what the interactions are, and that's actually what you really need to do in drawing a free body diagram, is think about interactions. So I want to actually be more careful than that. So we're going to draw this system diagram, and we're going to basically cut this bicycle and rider out of the rest of the universe. And that actually, when we cut them out of the universe, what we're really doing is freeing the body. Right? That's why it's called a free body diagram. It's a diagram of a body that is freed from the rest of the universe, and the way that it's freed is you sort of cut it out and then thought about what are the interactions that you've cut through in order to cut it out of the rest of the universe. All right, so I've cut out this bicyclist, and now I need to draw the bike again. Why did I do that? Oh boy, that's, wonderful bicyclist. But now that bicyclist is cut out of the rest of the universe, so it's free. But in cutting the bicyclist out of the universe, we actually cut through a lot of interactions. So let's think about what the next thing we want to do in making a free body diagram is think about what are the interactions that we cut through. In other words, in what ways does this bicyclist in person interact with the rest of the universe? Well, one thing that they clearly interact with is this bicyclist in person is a mass, right? So there's some mass, m1. And down here, way at the center of the Earth, is mass m2 of the Earth, and the Earth is pulling on the bicyclist via the gravitational interaction, right? So there's a gravitational interaction that pulls the bicyclist to the center of the Earth. Okay, that's one interaction. Okay? Pretty clearly, a second interaction is the ground is not allowing the bicycle tires to sink into the ground. right? The interatomic interactions are pretty strong, and they keep those bike tires on the surface of the road instead of allowing them to go down into the road. So a second interaction that's pretty clearly going to be present is a sort of normal force. And they're actually going to be a normal force at a couple of locations, right? They'll be at the front of the tire, the ground is going to be putting, on the front tire, the ground will be pushing up, and the back tire will be pushing up. So front and back tires, there'll be a normal force exerted by the ground on those tires. Finally, let's just assume that this bicyclist has just started riding, so they're accelerating. Well, what does that mean? That means there's got to be some force that's pushing them forward. And if you think about what that's actually got to be due to, what's happening is the bicyclist is turning this rear wheel and pushing it against the ground. There's a frictional interaction between the ground and the wheel, so the wheel pushes against the ground that way, the ground pushes back against the wheel this way, so there's a frictional force on the back tire, which pushes forward. In addition to that, probably there's some amount of frictional force on this front tire, which is actually causing that front tire to continue rotating. Presumably there's some amount of damping or frictional resistance in the hub, and so there's got to be, it's taking some amount of work for the ground to keep this front wheel spinning, so there'll be a little bit of friction on the front tire, and that'll be pointing back. Presumably this person is not biking through a vacuum, they're biking in the air, so you would imagine that a final force that might be present is actually they're moving through the air, and so there might be some drag force acting as well. All right? So we've got a list of interactions here. We can also think about what they depend on. The gravitational force is going to depend on what the mass of the rider is, right? The normal force is actually going to be pretty complicated because you've got two contact points, but nominally we'll say that's going to depend on the mass and could depend on whether the rider is moving in particularly interesting ways. So if the rider is accelerating vertically, like going through a curve, going up a hill or down or over the crest of a hill, the frictional force on the back tire and on the front tire are going to depend on what the normal force is, right? So these things will affect that, but also are going to depend on how hard the rider is torquing the wheels, or conversely how much the bike is accelerating, and the drag will depend on what the velocity of the rider is, right? So we've got some general idea of what the interactions are and how they behave. We've identified the interactions. We've cut the rider and bike out of the rest of the universe. And so now the last thing we have to do for our free body diagram is actually draw in what some of those interactions look like. And to draw them in, we think about two things. One of the things we think about is what's the direction. Actually, we think about three things. Think about direction, think about how big the different interactions are. Like are some of these big or some of these small? And finally, think about where they operate. Okay. So let's go down the list. Gravity. Gravity is going to act at the center of mass of the person-bike system. So nominally, let's say that's about here. Gravity pulls them down. Assuming that the rider is not accelerating up a hill or going over the crest of a hill or something, the total normal force will be equal to mg. And nominally, you might expect that that total normal force might be somewhat evenly distributed between the two tires. So there'll be a normal force at the front and a normal force at the back. And probably I should have made those arrows a little bit smaller, or the gravitational arrow a little bit bigger, so that this and this are about the same, added together about the same as gravitational force, since that would result in the person not falling into the ground. The drag force, let's see, so now we need the friction forces on the front tire and the back tire. The friction on the back tire is what's accelerating the rider forward, so that's going to be a relatively big forward force. So I'll call it F sub B for friction on the back. And on the front, there probably is a much smaller force, F sub F, That's that friction on the front tire that's causing the front tire to continue spinning. Finally, the drag force will be acting someplace, we'll be acting at the center of pressure of this person, which will be someplace close to the center of mass about, so I'll call that F sub D. And I've now drawn something that is not saying that the person is accelerating forward because I've made the drag force larger than the net frictional force forward, so probably I should actually make my drag force be back and be smaller, like so. And at this point I would say, okay, well the drag force looks like it's about the same size as F sub B plus F sub F, so it looks like it's actually not accelerating very much forward, and it looks like the total gravitational force is pretty much offset by these normal forces, so nominally it looks like this person is moving at a constant speed. So that's an example of building a free body diagram and being kind of careful to make sure that the size of the arrows are appropriate, that the directions of the arrows are appropriate, that the locations that they attach are appropriate, and being able to attach those arrows back to interactions that you can identify that you sort of had to cut through in order to release the body from the rest of the universe.